but I think I have not discussed the XRF part and also 31P NMR and silicon NMR. So that's why I have requested NPTEL team to provide me another one class. So today this will be not maybe 2 hours, and after the discussion XRF and NMR little bit whatever I have not discussed. If you have any question regarding whatever we have discussed starting from the first class, you may ask me. Okay. So let's start first the 31 phosphorus NMR. So we have discussed already proton NMR and 13C NMR. We have also shed light on solid state NMR. So today we will a little bit discuss about phosphorus and silicon. Now, why phosphorus is important? Because you know that though polymers are mainly carbon-based material, but still in polymer industry there are so many additives and more specifically flame retardant chemicals. Those are mainly phosphorus-based compound. So to uh, delve deeper, uh, whether the flame retardant how it works, you can go for the phosphorus and all. And before going to the details, just in introduction, that of course you know that to be NMR active, the uh, proton and neutron number it must be odd type. So 31P is magnetically active and it can give response in NMR. The gyromagnetic ratio that phosphorus has, it is 40.5% compared to your proton. And the most important thing is it is 100% isotope abundant. So there is no uh, problem regarding, for example, 13C, it is around 1 point something, the natural abundancy. But 31P, it is 100% abundant in nature. And on if you provide 11.7 Tesla magnetic field, external magnetic field, the 31 phosphorus nucleus will be detected around 202 megahertz. And phosphoric acid, that is H3PO4, is usually used as standard and its chemical shift is assigned as 0 for like TMS that we mainly used as a standard sample for proton NMR. In case of phosphorus, this is phosphoric acid, and this is an external standard due to the high reactivity of the phosphoric acid. Standardization can be done by inserting coaxial tube into the NMR sample tube or by using separate. So either in the same sample tube you may use both sample and the reference or standard phosphoric acid, either in another tube. In that case you will have two different tube where one tube will contain the standard phosphoric acid and another one will be your sample, but it is less sensitive as compared to proton and 13C carbon. 31P NMR commonly depend on the concentration of the sample, since the sensitivity is little bit less as compared to proton and 13C. The concentrations will be little bit higher as compared to your proton, and usually you should prepare your sample by uh, using 2 to 10 milligram of your sample and dissolved in a proper solvent, and then if you use that sample. If you compare the chemical shift, the range is minus 140 to 200. So that is a broad range where phosphorus can be detected in 13P NMR. And you see that if it is P or X2, where X is the halogen, the peak will be observed around 150 or 160 to 200 ppm. That is delta value. because of the electronegative atom is directly linked with the phosphorus. And in this case of phosphines, that is pH3, it will come around minus 100 or minus 150 to minus 100. Now the splitting, uh, like similar way in proton or 13C, the rule is n plus 1, that is proton number of atom bonded with it plus 1. So if it is pH3, it will be quadrate because of the 3 proton. So 3 plus 1 will be quadrate. This is showing here. If it is pF3, that will be also appeared as a quadrate. Now in case if it is PCl5, so there will be two different nature of the peak if it is in solution state or if it is in solid state. The reason behind that, if it is in solid state, now PCl5 not remain as PCl5 in solid state, it remains as a PCl4 plus because of it is the dimeric nature, and PCl6 minus. So that's why we will get a doublet type of peak in case of solid PCl5, but if it is in solution phase, we will get a singlet type of peak. Similar way, H3PO4 will be singlet, H3PO3 will be doublet, and H3PO2 will be the triplet. Now in case of PH2F or PH2F3, PH2F is doublet of triplet. Why? Because of one F, first P will be doublet, and then since there is also another two hydrogen, so that single doublet will be again splitted into triplet because of the 2 plus 1. So first step, it is disintegrated into n plus 1, that is 1 plus 1 2 doublet. Now again there is two hydrogen is directly bonded with the phosphorus, so this is doublet because of the fluorine, this one and this one. After that, because of the two hydrogen, again this doublet will be splitted into triplet, so that's why it is doublet of triplet. Similar, so in PH2F3 it will be quadrate of the triplet. Since F3, so 3 plus 1 4 quadrate, and again that quadrate will be splitted into triplet because of H2, that is 2 plus 1. Now similar, so here is also decoupling is important, and for that you must be proton decoupled technique should be used to get more resolution or more uh, clarity in the peak, and integration in accurate due to the uneven NOE enhancement of the signals by decoupling, because whenever you are doing the decoupling, so the intensity will be little bit reduced. This is proton decoupled, this is proton coupled, that's why you are getting two peak. When that proton coupling is gone, you will get the single peak, that is because of the proton. Now what are the different application of 31p NMR? As I have already told, that since all polymeric material are usually carbon or hydrogen based material, but since there are some uh, polymers, but that is very few, for example polyphosgene or polyphosphagene, but rest importance, that is there are so many flame retardant additives, those are used for different fire retardant application where phosphorus based chemicals are used, and also other plasticizers or other different additives where phosphorus is used. So first of all, it will provide a sharp peak indicating the presence of a mixture of free phosphorus containing contaminants. To ascertain a chiral sample, chirality, that is very important in organic chemistry. Uh, that but we should not go in very details because chirality itself it's a huge syllabus. So the formation of two distinct diastereomers by adding enantiomer to the chiral mixture will result in two distinct chemical shift in the 31p spectrum. Now the optical purity can then be calculated by comparing the ratio of the height of these two different peaks. And next is the, if someone try to study the kinetics of a reaction, how the phosphorus intensity is changing, that can also be done through the NMR. For example, if uh, somebody is going for block copolymer or a two different monomer ETPPN, that is 2-ethyl 2-oxo 132 dioxaphospholene with TMC, that is trimethyl carbonate, then with time how the reaction is going on, that can be studied through the NMR. Now real time 31P NMR kinetics for the copolymerization in ETPPN2 and with TMC, and A is the overlay of the 31P monomer of the copolymerization, and B is the chemical structure of the four different triads. Triads means this one block is called the triad. This one block is the triad. Now how the intensity of this P is increasing, that can be monitored with time. That means during the reaction you take out the sample, do the 31P NMR study and check how the intensity is changing. In that way you can study the kinetics of the reaction, that how much concentration is changing with time. Next is the determination of the phosphorus containing flame retardant. So this is very much important. So first, this is the starting material. You use this chemical as a flame retardant. So first take the NMR of these additives, and after that when it is reacting, so after this three step, ultimately it will form the DHP. This is the chemical name of the DHP, and you see after that three step there will be the appearance of another peak around 0 point something. So this study can also be done and only possible through 31P NMR. You cannot do this study with 13C or proton NMR. The next is the silicon NMR. A 29 silicon magnetic moment is slightly lower than 13C. This leads to the lower resonance frequency. The spin and magnetic moment are antiparallel, leading to a negative sign of the gyromagnetic ratio. Thus, silicon NMR had a slow start. That means actually it is developed after 13C and proton and 31P. And 29 silicon has a natural abundance of 4.7%. That is also a disadvantage. A spin of plus half, a magnetic moment of minus 0.9609, and therefore the receptivity of 3.69 10 to the power minus 4 compared to that of the proton. It can be characterized as a magnetically diluted isotope of medium sensitivity. So if you compare proton 13C and 29Si, so 29Si is little bit uh, low, or it has very dilute sensitivity as compared to your proton and 13C because of its low natural abundancy, as well as it has a very negative gyromagnetic ratio. Now, there are different standard of silicon based sample. So as we know that TMS is used for your proton NMR 1H NMR. Here you can also go for the trimethyl silane because it has low boiling point, relatively short reduction time and inert substance. But the problem is its resonance is in a shift range where resonance of many other organosilicon compounds occur. So that is the problem. If you use the TMS as a standard for silicon NMR, the problem is other peak that will also come around that TMS. That's why it will be difficult to analyze the, or it will misinterpreted you to analyze perfectly. So that's why you should go for other different standard. And the most deshielded silicon, the delta value will be plus 268, and the most shielded one, the delta value will be minus 351 ppm. So that is a very vast shift are found in between 150 ppm to minus 200 ppm. If you compare proton 31p and 13c. So delta value will be the broadness will be of the delta value will be very high in case of 29 Si. Coupling with 100% isotopes such as proton 19A for 31p gives the well-known splitting pattern of the 29 Si. So with silicon, if there is proton or fluorine or phosphorus is bonded, it will split the peak. And coupling with other rare spin, for example tin or 13C, leads to smaller satellite lines left and right to the main line. So this will also create some complexity in the NMR spectra. The application part of 29 SI in NMR, solid state NMR, this is very important. For example, we know that if there are different clay material or silica that used in tire industry or other polymeric industry, so there are different type of silica, mainly two different type of silica material is used as a filler. One is the precipitated silica, one is the pyrogenic silica. Pyrogenic silica, that is actually processed at a very little bit higher temperature as compared to your precipitated silica. Now the 110 ppm shift has been assigned to the SiO silicon atoms, and the 100 ppm resonates to single silanol, that is SiOH bond, and minus 90 ppm is geminal, that is Si with 2 hydroxyl. Now how many hydroxyl group are present, or how the silicon is bonded with your other silicon atom or which, that can be easily determined by study the 29 SiNM analysis. Now the importance, why it is very important, because we know that the presence of hydroxyl group that will ultimately dictate the coupling with different sealant material. So obviously that will affect the ultimate adhesion property or mechanical property of the final product. Now that study could be done through 29 SI, that how many SiOH are present by checking, because you see the peak position is different when Si is bonded with another oxygen or another Si atom. A resonance of pure unreacted coupling agent is observed at approximately 46.5 ppm. The silicon atoms of mono, bi and trisubstrate alkynyl triethoxysilanes have chemical shift approximately minus 49, minus 58 and minus 56. Now this is also very much important, because whenever the side or end group will be a phenyl or phenyl group, and if Si is bonded with that phenyl carbon or aromatic phenyl carbon, the delta value will be different, and that end group will also actually dictate the cross-linking when you will final process the material. So that's why 29 silicon NMR is very much important for the polymeric type of or composite type of material. So this is the polysiloxane NMR of a polysiloxane material. So the SiA is bonded with 2 phenyl ring, and then next Si is bonded with 2 CH3. The C and D also bonded with 2 CH3. Now copolymer of polydimethyl siloxane and PDMS and polydiphenyl siloxane PDPS. So if this is a 3 blocks are present, so you will get F1, F2 and FC. The delta value is corresponding to minus 21 to 22, minus 2. Those are almost very close by, but still there are some small peak that appear because of the different electrical environment surrounding the silicon nucleus. So those were the NMR part that I have not discussed during the NMR lecture series. The next is the X-ray fluorescence. So we have discussed in XPS, X-ray photoelectron spectroscopy. We have also discussed XRD, but XRF we have not discussed in. So we have already discussed vividly that whenever there is a incident radiation, what are the different electrons came out from the sample. There is auger electron, there is secondary electron or backscatter electron. So different type of electrons came out. Now X-ray is a non-destructive analytical technique. So one of the phenomena is the X-ray fluorescence. Whenever there is a incident radiation is uh, collide with the material, so these phenomena can also be possible, and that X-ray is coming as a fluorescence. So we will discuss that how X-ray is generating in next slide. So this is basically a non-destructive analytical technique, though it is not 100% true, because whenever there is a incident X-ray beam, so there may be some electrons are knocks out. So of course there is a formation of ions. So in that sense it is not a non-destructive, but since you are using very small amount of material, so in that way you may say it is a non-destructive technique. Now it is the emission of a characteristic secondary or fluorescent X-ray from a material that has been excited by being bombarded with high energy X-ray. So whenever there is a high energy X-ray, it will eject the K cell electron, and whenever there is a ejection, so there is a formation of the uh, vacancy. To fill up that, the higher energy electron will come down to the lower energy cell, and that excess energy will be emitted as a X-ray fluorescence. Now it can provide both a quantitative and qualitative analysis of elements, and it can detect concentration from 100% down to ppm level, and it is recommended for materials where matrix effects are not relevant. Now since this is inherent property of a atom to atom, so it is recommended that where matrix effects are not that much relevant, because from matrix if it is generating, then it will be little bit problem. Now when radiating an atom with X-ray photon, once again it can expel an electron from the uh, lower cell that is close to the nucleus and creates a hole or vacancy in inner cell. Now to fill up that, from outer cell it will, and another electron will come down, and when it is come down, that excess energy will be emitted as a X-ray photon, and it will be visible as a line spectra. The collection of the emitted lines is characteristic of the element and can be considered a fingerprint of the element. Now since of course atom to atom the energy level will be depend, so from a single atom, of course a single uh, or you may say a specific energy of X-ray fluorescence is possible. So from different atom there will be different energy X-ray will be, or X-ray fluorescence will come out. The characteristic radiation produced directly by the X-ray coming from the source is called the primary fluorescence, while that produced in the sample by primary fluorescence of other atom is called the secondary fluorescence. So that incident X-ray, it must have the higher energy, then only it can eject out or knock out the electron, and that produced in the sample after the primary fluorescence, that will be the secondary fluorescence. To expel an electron from a atom, the X-ray must have a, of course, higher energy compared the higher energy level than the binding energy of the electron. And the higher the radiation absorption by the atom, the higher will be the fluorescence. That is of course true. Higher will be the absorption, so there is a much more chance to eject out a greater number of electron, and obviously then there will be the higher probability to get higher intense fluorescence or higher uh, intensity of the fluorescence. If the energy is too high, then many photons will pass the atom and only a few electrons will be removed, therefore produce low fluorescence. This is very important. So if one may think that if I am uh, irradiating the material with a very high energy, then the intensity will be very much high, but it is not true. Now the reason is, in quantum, this is the most important thing is the energy difference should not be very much high. So whatever the energy it can absorb, or if the binding energy of the K cell, let's say it is 5 electron volt, so you cannot uh, irradiate the material with 10 electron volts. You just provide energy little bit higher than the 5, so maybe it is 5.1 or 5.2, then only you will get the better or higher intensity X-ray. The highest yield is reached when the energy of the photon is just above the binding energy of the electron to be expelled. Otherwise, what if you provide very high energy? So it will not eject out, rather it will pass through the nucleus. The K edge corresponding to the K cell and 3L edge corresponding to the L1, L2 and L3 cell. So this is just surrounding the nucleus, there is K, L, M. So whenever K cell electron is ejected out, it is a K edge. If it is from L, then it is L edge. And if the energy becomes lower than the binding energy, a jump or edge can be seen. The energy is too low to expel the electron from the corresponding cell, but is too high to expel the electron from the lower energetic cell. Now the magnitude of the absorption, it depends that the energy of the radiation, of course, that if it is too much high, it cannot absorb too much, it will pass through the nucleus. And next is the path length. So if this is the D, and if it is incoming X-ray is coming here, and from this from here the atom is present, it is ejecting out, so that also depends on the energy of the incident X-ray and how much depth it can penetrate. The next is the density of the sample. So higher will be the density, the absorption will also vary. The atomic number, of course, if it is XRF is much more prominent for higher atomic number element as compared to your lower atomic number, and that's why for lower atomic number element you should study the agar electron rather than XR. Only higher atomic number elements will uh, more intensely it will generate the XRF. Now there are two forms of XRF, so that is basically the detector part, where one is the energy dispersive and another is the wavelength dispersive. So one detector, it can study the energy of the XRF, and another detector type that can study the wavelength of the X-ray. Now how? Because we know there is a duality, both the particle nature and wave nature of the material. So in case of energy dispersive, that means it is studying the particle nature of the photons. Those are coming out as a X-ray or fluorescence. On the other hand, the WDXRF, where it is studying the wave nature of the photon. So the energy dispersive detector treat the X-ray as a particles here, and they work like throwing a bowling ball, the photons, into a ball pit, the detector, to see how many small plastic balls are ejected out. By each impact, a heavier or faster bowling balls, that is higher energy photons, will cause more plastic balls to be ejected. This method generates XRF spectrum by counting and plotting the relative X-ray at each an energy point, and it is a rapid method, repeating the analysis at a very high rate before sorting the result into different energy channels. So this is the ET X-ray. So where after primary X-ray is colliding with the sample, then directly it is going to the detector and then amplifier, after that pulse height analyzer. On the other hand, wavelength dispersive, this is little bit complex. So of course this is the resolution will be less in case of energy dispersive X-ray, but it is fast analysis. But in case of wavelength dispersive X-ray, where a wavelength dispersive spectrometer treats the X-ray as a wave and uses some regular structure or gratings or crystal to focus it, and can cause interference pattern that allow remarkably higher spectral resolution. And wavelength dispersive X-ray offers a higher resolution, making it suitable for analyzing more complex samples. Obviously, The higher the resolution, we can analyze complex sample, and you see the complexity little bit a bit higher as compared to the EDX type, where solar slit first the XRF or X-ray fluorescence is coming out. Those are passing through a solar slit, then dispersive crystal to uh, cause the interference or focus it, and again through another solar slit. After then it is coming to the detector part. That's why if the sample is very much complex, one should go for the WDXRF to get more resolution. On the other hand, if it is a simple structure and one can trying to study the fast, or he wants to get a result very fast, then he or she should go for the energy dispersive X-ray. Direct and polarized energy dispersive X-ray. So this is the basic structure, where benchtop energy dispersive X-ray fluorescence spectrometers are very compact in size and have a relatively simple setup. The silicon drift detector, this is the silicon drift detector SDD, records the entire energy spectrum at once, and thus multiple elements can be detected simultaneously, but obviously the resolution will be low. Direct EDXRF spectrometers are used for closely coupled beam path to pressure to measure major, minor, and trace elements in all kinds of liquids, powders, grains, solids, and bulk. So it does not depends on uh, the sample phase or sample morphology. And polarized EDXRF spectrometer utilize monochromatic X-ray to enhance single signal to noise ratio. So there is a single wavelength X-ray is used, so that the chance of getting higher noise signal to noise ratio will be less, like sulfur, phosphorus, and chlorine in petrochemicals, to achieve ultra low detection limits even with a compact device. And obviously you need a HD video camera here. So through here, this is the X-ray tube generating the X-ray, the filter wheel, then obviously collimator to make a monochromatic light. This is the sample, and after that the detector is here that will detect the energy of the generating X-ray. Now, wavelength dispersive WDXRF is more sophisticated and of 1 to 2 orders more sensitive than the energy dispersive X-ray, where it contains powerful X-ray tube up to 4 watt, several optical components, that is filter, collimators, and analyzer crystals to separate X-ray photons emitted by the sample based on their wavelength, and that also depends on the Bragg's law. Sequential floor standing WDXRF and benchtop WDXRF system spectrometers has a goniometer to change the angle and crystal type for each wavelength, since it is measuring the wavelength. So of course the uh, angle and changes the crystal type, that will affect, and that is the elemental concentration can be measured sequentially through the WDXRF. In micro XRF, this is one another kind. This technique is used a polycapillary optic to guide the excitation X-ray into a micrometer size spot on the sample. Now you know that since X-ray you cannot change the angle through the lens, so that's why you need some polycapillary type optic to guide the excitation or to focus it in a single spot on the sample. Through lens you cannot do that because of the refractive index is almost equal in air and as well as in glass. Thus it cannot only tell you what elements are in the sample and how much of them, but also, so that is the beauty. It is not only you give the information about the uh, different elements and the quantity, but also exactly where the elements is located, that can also you can study. Especially when combined with fast scanning sets, this method is ideal for measuring and understanding inhomogeneous sample with micro X-ray, and almost any kind of sample can be measured. So that is the advantage of the micro X-ray. So you will get both the quality, quantity, as well as the distribution of the element in a sample. So this is the table of summarizing of different X-ray spectroscopy, X-ray diffraction, Auger electron spectroscopy, transmitter electron microscopy, and X-ray. So we have discussed the what is the method. And if you check the depth profiling and lateral resolution, so XRF depth sensitivity using microcapillary lenses and confocal technique, lateral mapping at high resolution with synchrotron source, but crystallography cannot be possible through XRF. That means how what type of crystal or what is the unit cell you cannot get the information from XRF. But elemental analysis you can of course do even microgram to gram level sensitivity for many elements, so and quantification often hard. In case of XRD, of course the crystallography it is very powerful, so usually XRD are used to uh, know more details about the crystal structure, crystal nature, and elemental analysis also possible, but that is indirect method. Indirectly we can also determine what are the different elements present. In XPS we cannot understand the crystallography part, but yes, elemental analysis can be done through XPS. Actually, what are the different elements present in a sample? Very accurately one can determine. Auger electron spectroscopy, that crystallography cannot be possible through Auger electron spectroscopy, but elemental analysis. So in if you compare XRF and AES, so obviously uh, higher atomic weight element will be much more uh, give you prominent result in XRF by studying the XRF. Whether Auger electron study that is usually done for the low atomic weight element. On the other hand, TEM, so it is very powerful regarding the crystallography information, and also elemental analysis could be done with EDAX and EELS, usually semi-quantitative and represented as always a constant. So that is a disadvantage of the TEM, but still we can do through EDX and EELS. So this is the anatomy of the XRF. So you need a X-ray tube, a secondary target, a detector, and multi-channel analyzer. So secondary target, that tube irradiates the secondary target, and this target will emit its characteristic radiation. The advantage of a secondary target is that it emits almost monochromatic radiation, but its disadvantage is, of course, whenever uh, there is a secondary target, so there must be a loss of some energy, and using different secondary target one can achieve optimum excitation for all elements. So if there are a large number of different elements present, so then it will be helpful. There are three types of secondary target: fluorescent target, Barkta target, and Bragg's target. Detector, we have already discussed the energy dispersive and length dispersive XRF detector. So ED XRF mainly use solid state detector, where WD XRF used gas field detector and scintillation detector. The energy dispersive X-ray detector is a wide range of detector to measure the various elements present in your matrix from sodium up to uranium, and gas field detector measure elements from beryllium to copper, and the scintillation detector from copper to uranium. All these detectors produce an electrical pulse when a X-ray photon enters the detector, and the height of this pulse is proportional to the energy of the incoming photon. The pulses are amplified and then counted by a multi-channel analyzer. So that is the mechanism of the detector, how it is detecting. Now multi-channel analyzer, a WD XRF only has to count the pulse, says number of pulses are coming, and does not have to distinguish between their heights, because the crystal has already selected X-ray with one specific energy. In practical situation, the multi-channel analyzer for a WD XRF detector is able to distinguish 100 to 255 So this is you just check that how many different energy level it can distinguish at a single time. 100 to 255 different energy level it can be possible. And in energy dispersive X-ray spectrometer, the detector and MC are able to distinguish between 1000 to 16,000 different energy level. This is sufficient to analyze the spectra to separate the radiation from the various elements. So, of course, since it depends on the elements to elements because of the different atomic weight and different the energy of the cell. So, at a time from different elements, there will be a generation of different wavelength of the X-ray. But through this, we can detect that much different energy level at a single time. Now, in terms of lens, actually lenses are used in X-ray to focus the X-ray on a crystal, but this is not like the glass type of uh, convex type of lens because the refractive index it is already highlighted here to receive only fluorescence from a small spot. Visible light has a refractive index higher than 1, so a convex glass can be used to focus the light. But since X-ray have a refractive index just below 1, so to achieve the same effect, the lens should be concave because the diffractive index is very close to 1. And another thing is the focal distance is very long, that is 1 meter. So obviously it is not suitable for a practical purpose. And another way to focus X-ray is to use the capillaries. So those capillaries are the basically glass fiber capillaries, hollow glass fiber capillaries. Because the difference in refractive index, visible light would require solid glass fiber. A monocapillary has one fiber and a polycapillary has a group of fibers. So because of this group of fiber, the X-ray are scattered in the fibers and all are focused on one spot. But this is a little bit complex that how the glass fiber, the group of fibers are arranged so that after scattering that X-rays will be focused on a single spot. But you cannot do that just by using the convex lens. But that is possible for visible light because of the higher refractive index in the glass. It is around 1.5, but it is in air. Visible light has refractive index 1. But since X-ray are below 1 or very close to 1, so that's why it is difficult to focus just by using the convex lens. That's why you need the capillaries, multiple capillaries. The focal distance and the transmission of the lens is not the same for all energy. Very low energy are absorbed by the lens and very high energy are not focused but just pass through the lens. That's why uh, glass capillaries are used to focus the X-ray. Now next come to the peak analysis part of the X-ray. So the first step is to analyze or determine the top position and the area of the line profile. So the position of the tops represent the presence of elements, and for different elements you will get a different peak position will be different, and the area will represent the intensity of the line. So peak search and peak match, for that you need the database for example when you are matching the XRD data, so you have the database where you will check the card number, JCPTS card number for each and every uh, material. The similarly to the peak search and peak matching can be done just by checking the database holding the position of all possible lines. And next thing, if two peaks are very much merged with each other, then you need the deconvolution. So deconvolution is used to determine the area of the individual peak. So that means whenever two different peaks are merged with each other, in that case you need the deconvolution part. So that is a mathematical method called the least square fitting or theoretical calculation, the ratio between the groups of lines and intensity. So XRF has very wide application area. For example, catalyst monitoring in polymerization process. So of course, whenever a catalyst is uh, catalyzing a reaction, and after that you can check that how much uh, catalyst is remained in your material, or what are the different during the reaction, how the kinetics is going on. That can also be done through X-ray. To verifying additive level in polymer, so obviously there are different zinc or phosphorus based additives, those are used in polymers, and how much levels are present in your uh, composite material, that quantitatively you can determine through XRF study. The analysis of plastic and recycled plastic, that study also possible through XRF. Bulk chemical analysis of major element, those are high atomic numbers, silicon, titanium, aluminum. In rock and sediment, these analysis, chemical analysis can also be possible. Bulk chemical analysis of trace elements in abundance is greater than 1 ppm in rock and sediment, that means in solid type of material. And detected elements for trace elements are typically on the order of few parts per million. So even 1 ppm can also be detected through the XRF study. So that's all about today's discussion. Uh, Mainly these two part in 30 NMR part 31P and 29 silicon, and in different X-ray characterization technique we have not discussed previously XRF. Uh, Now if you have any question regarding your polymers or composite or different characterization, starting from our first class, where we have discussed structure property relationship, uh, different molecular weight, glass transition temperature, and then we have discussed different FTR spectroscopy, FTR UVVs. After that, we have discussed NMR spectroscopy. Then we have also shed light on X-ray characterization technique, that is a combination of XRD, XPS, SAX, and XRF. Today we have finished the XRF part. We have also discussed vividly the electron microscopy, electronic microscopy, that is FESM and TEM. Other microscopy you have also discussed optical microscopy, and then AFM. And finally, last day we have discussed the separation technique, that is chromatography. Mainly we have discussed GPC, gel permeation chromatography, and HPLC, high performance liquid chromatography, how they separate actually. So if you have any question or queries regarding any characterization technique we have discussed, you may ask me. I hope you have a little bit understanding after this 12-week course. I have tried my best, though maybe I have not fulfilled all your demands. Sorry for that. And of course, I am also thankful for your question during classes and your patience. So it will be uh, my pleasure if you uh, ask me something regarding our previous discussion, or uh, other type of question also you may ask. So, Nair sir, are you there? Thank you for your compliment. No issue. Yes. Still, I will suggest you that if in future you have any doubts or queries, you may mail me. I will surely answer you. Okay, okay, okay. No, 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 sir. No, sir. It's not disturbing. It's not disturbing. Still, I am okay with that. Whenever you want to discuss something, regarding any topic, you may call me or you may mail me. Uh, Certainly, I'll respond. Okay, okay, uh, okay, 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 okay. Thank you. Sure, 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 sure. I'll do that. So, I will just, sure, sure. So, I'll just suggest all of you who are working or who are still in academic. I don't know how many people are in academic, but those who are engaged with polymeric type of material in whether it is in industry or in academics, you must should have knowledge to at least in structure property relationship. How you can assume that if the structure of my material is this, then what property I should guess and how I can modify further those properties. That is very, very important in polymeric industry as far I experienced it, because before interning in PhD, I have also spent a little bit time in industry. So that is very, very important. And more specifically, I will say that in polymeric industry, thermal characterization is very, very important, and another part is the mechanical property. So how you can tune the mechanical property just by observing the structure, that is very important, and you should uh, get the knowledge that how one can assume that okay, if this is the structure of my material, what are the different chemical modification I can do so that my property will improve, the rheological property will improve, because the processing is very important. That will ultimately dictate the final property. Even if your formulation is very good, but still if you cannot control the process parameters, that will create the problem. And from structure property relationship, that's why I am uh, so many times I have asked my friends or my juniors or my colleagues during my industry time that by knowing the structure, I can at least guess that what will be the problem if processing parameters are changing, at least. And next thing, if you ask about the microscopy, that is also very much important, but still you also know better than me that electron microscopy is not that much available because of it is very, very sophisticated, and also the cost. If you check the cost of a FSM or TM, that is very much huge, and it is really difficult uh, to uh, uh, buy it for a small type of industry. But yes, one can go for the TG or DSC. That is very important also. By looking at TG, you can also guess that what will be the abrasion resistance, what will be the hardness, So that much knowledge if someone has, then he or she can uh, a little bit advanced compared to others. Anyway, I think if I've enjoyed the class and still if you have any doubts, I have already shared my email ID previously. You may contact with me and I will try to my best to catch you in near future. So thank you all once again and I wish all of you uh, a better and healthy future. So right now I am uh, closing it here. Okay, welcome, welcome. Done. Okay, meeting. हो गया विवेक मीटिंग हाँ विवेक मीटिंग कहाँ चलते हैं चल 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 अच्छा है बस हो गया आपके विवेक और बताऊंगा मैं नहीं इसीलिए चला इधर आ गया क्या इसीलिए सच दरबार लेकिन ना हमारी सर के ना बिहेवियर में चेंज आ जाता है पता है मुझे क्या रिकॉर्डिंग